The cosmos, a vast canvas of darkness sprinkled with the brilliant light of billions of stars. From ancient civilizations to modern astronomers, we have always sought to understand our place within this grand cosmic tapestry. In the 20th century, our understanding of the universe underwent a revolution. Edwin Hubble's observations revealed that distant galaxies were moving away from us, implying that the universe itself was expanding. This discovery suggested that the universe must have had a beginning, a moment in time when all matter and energy were concentrated into an infinitesimally small point known as the Big Bang. The early 20th century marked the birth of modern cosmology. Edwin Hubble's work provided the first concrete evidence that the universe was expanding. Albert Einstein's general theory of relativity predicted that the universe could not remain static, but must either be expanding or contracting. Edwin Hubble's discovery that the universe is expanding was a pivotal moment in science. Using the Hooker telescope, Hubble observed that galaxies appeared to be moving away from us, and their speed of recession increased with their distance. This relationship, now known as Hubble's law, was the first empirical evidence supporting the idea that the universe is expanding. The realization that the universe is expanding revolutionized our understanding of cosmology. This expansion can be visualized as the stretching of space itself, with galaxies embedded in this expanding fabric. The expansion of the universe is not uniform. It has been influenced by various factors over time, including cosmic inflation and dark energy. The Big Bang theory is the prevailing cosmological model explaining the origin and evolution of the universe. It posits that the universe began approximately 13.8 billion years ago from an incredibly hot and dense state and has been expanding ever since. The Big Bang theory left some significant mysteries unsolved, such as the horizon problem. The cosmic microwave background radiation shows that the early universe had an almost perfectly uniform temperature. This uniformity is puzzling because regions of the universe separated by vast distances would not have had enough time to interact and reach thermal equilibrium. In the early 1980s, physicist Alan Guth proposed cosmic inflation to solve the horizon problem. This theory posited that in the first fraction of a second after the Big Bang, the universe underwent a period of exponential expansion. This rapid expansion smoothed out any initial irregularities and explains the remarkable uniformity of the cosmic microwave background. Cosmic inflation explains the uniformity of the CMB, the origin of large-scale structure and the flatness of the universe. The theory's predictions about the properties of the CMB have been confirmed by observations with remarkable precision. While some critics argue that it relies on speculative physics, the theory's ability to explain several puzzling features of the universe has made it the leading paradigm for understanding the earliest moments of the universe. The inflationary epoch, though fleeting, left its imprint on the universe in subtle ways that astronomers and physicists are now working to decipher. One of the most promising avenues for studying inflation is through the search for primordial gravitational waves. These ripples in spacetime generated during inflation would have propagated through the universe, carrying with them information about the energy scale and other properties of the inflationary epoch. These primordial gravitational waves would have interacted with the CMB, leaving a unique signature in its polarization pattern. This signature, known as B-mode polarization, would be a smoking gun for inflation and provide invaluable insights into the physics of the very early universe. Detecting these faint signals, however, is a formidable challenge. In 2014, the BICEP-2 collaboration announced the detection of B-mode polarization in the CMB. This discovery, if confirmed, would have been groundbreaking, providing the first direct evidence for inflation and opening a new window into the universe's first moments. However, subsequent analysis revealed that the signal was likely contaminated by dust in our own galaxy, highlighting the difficulty of teasing out these faint signals from the cosmic noise. Despite this setback, the search for primordial gravitational waves continues with renewed vigor. New telescopes and experiments are being developed with increased sensitivity and better foreground removal techniques, holding the promise of finally detecting these elusive echoes of the inflationary epoch. Section 5. Inflation and the multiverse. Perhaps one of the most mind-boggling implications of cosmic inflation is the possibility of a multiverse, a vast ensemble of universes, each with its own unique properties and laws of physics. This idea arises from the realization that inflation, once started, may never completely stop. Instead, it might continue in some regions of space-time, creating an ever-expanding sea of inflating space. Within this inflationary sea, quantum fluctuations could cause pockets of space to drop out of inflation, forming bubble universes like our own. Each bubble universe would then evolve independently, potentially with different values for fundamental constants like the strength of gravity or the mass of the electron. The concept of a multiverse is highly speculative and remains a topic of intense debate among physicists. There is currently no direct observational evidence to support it, and it may be impossible to test definitively. However, the idea arises naturally from our understanding of inflation and quantum mechanics, and it offers a tantalizing glimpse into a reality far grander and more complex than we could have ever imagined. Whether the multiverse exists remains an open question, one that may forever lie beyond the reach of scientific inquiry. Nonetheless, the very possibility challenges us to expand our conception of reality and our place within the grand cosmic scheme. Section 1. Ripples in space-time. Imagine tossing a pebble into a still pond. The impact creates ripples, concentric circles that spread outward. Similarly, massive objects accelerating through space-time create gravitational waves. These waves, predicted by Einstein, are disturbances in space-time itself. Gravity is a curvature of space-time caused by mass and energy. Accelerating massive objects create ripples that propagate at the speed of light. Detecting these waves is an extraordinary technological challenge. Gravitational waves offer a new way to observe the cosmos. Section 2. The search for gravitational waves. The search for gravitational waves has been a decades-long endeavor, pushing the limits of engineering and scientific ingenuity. The challenge lies in detecting the infinitesimally small distortions in space-time caused by these waves. To put this challenge in perspective, imagine trying to measure the distance between Earth and the Sun to the width of a human hair. The first attempts to detect gravitational waves began in the 1960s with the pioneering work of Joseph Weber. Weber designed and built resonant bar detectors, massive aluminum cylinders that would vibrate if a gravitational wave passed through them. While Weber claimed to have detected gravitational waves, his results were never independently verified, and his detectors were not sensitive enough to detect the faint signals expected from astrophysical sources. In the 1970s, a new approach emerged: laser interferometry. This technique, far more sensitive than resonant bars, relies on measuring the minute changes in distance between mirrors caused by the stretching and squeezing of space-time as a gravitational wave passes through. The Laser Interferometer Gravitational Wave Observatory, or LIGO, with its 2 detectors located in Hanford, Washington and Livingston, Louisiana, was built based on this principle. LIGO's detectors consist of 2 4-kilometre-long arms arranged in an L shape. Laser beams are bounced back and forth between mirrors at the ends of each arm, and their interference pattern is precisely monitored. If a gravitational wave passes through, it will stretch one arm while squeezing the other, creating a tiny shift in the interference pattern. This shift, though incredibly small, can be detected by LIGO's highly sensitive instruments. On September 14, 2015, LIGO made history. Its 2 detectors, separated by thousands of kilometers, simultaneously observed a gravitational wave signal, confirming a century-old prediction of Einstein's theory and ushering in a new era of astronomy. The signal, designated GW 150914, originated from the merger of 2 black holes, each about 30 times the mass of our Sun, located over 1 billion light-years away. The signal was incredibly brief, lasting only a fraction of a second, but it carried the unmistakable signature of a binary black-hole merger. As the 2 black holes spiraled closer together, they emitted gravitational waves with increasing frequency and amplitude, culminating in a final burst of energy as they coalesced into a single, more massive black hole. This final burst of energy, equivalent to 3 times the mass of our Sun, converted instantly into gravitational waves, shook the fabric of space-time, sending ripples that travelled across the cosmos for over 1 billion years before reaching Earth. LIGO's detection of GW 150914 was a watershed moment in the history of astronomy. It provided the first direct evidence for the existence of black holes, confirmed a key prediction of Einstein's general theory of relativity, and opened up a new window on the universe. For the first time, we could listen to the symphony of the cosmos, not through light or any other form of electromagnetic radiation, but through the whispers of gravity itself. This discovery sent shockwaves through the scientific community and beyond. It was hailed as one of the greatest scientific achievements of the century, earning the 2017 Nobel Prize in Physics for Rainer Weiss, Kip Thorne and Barry Barish, the pioneers who made LIGO a reality. LIGO's groundbreaking discovery has ushered in a new era of gravitational wave astronomy. Since the detection of GW 150914, LIGO and its European counterpart Virgo have observed dozens of gravitational wave events, each providing valuable insights into the most energetic phenomena in the universe. These observations have revealed a population of black holes more massive and diverse than previously imagined. They have also provided the first direct evidence for the existence of binary neutron-star mergers, cataclysmic events that produce not only gravitational waves, but also powerful bursts of gamma rays, X-rays, and visible light. The simultaneous detection of gravitational waves and electromagnetic radiation from these events, known as multi-messenger astronomy, has opened up exciting new avenues for studying the universe. Gravitational wave astronomy is still in its infancy, but it has already revolutionized our understanding of the cosmos. It allows us to study objects and phenomena that are invisible to traditional telescopes, providing a unique and complementary perspective on the universe. As gravitational wave detectors become more sensitive and new telescopes come online, we can expect a steady stream of discoveries that will continue to reshape our understanding of gravity, black holes, neutron stars, and the evolution of the universe. Gravitational waves offer a glimpse into the most extreme environments in the universe, where gravity reigns supreme and the laws of physics are pushed to their limits. By studying these waves, we are probing the fundamental nature of gravity and the structure of space-time itself. Section 5. The Symphony of the Universe. The detection of gravitational waves has been likened to the moment when humanity first opened its ears to the symphony of the universe. For millennia, we have gazed at the cosmos, captivated by its beauty and mystery. But until recently, we have only been able to observe the universe through a limited range of electromagnetic waves, like listening to a symphony while only being able to hear a few notes. Gravitational waves provide a completely new way of listening to the universe, one that reveals an entirely different set of instruments and melodies. They allow us to hear the deep rumblings of black holes colliding, the chirps of neutron stars spiraling towards their doom, and perhaps even the faint whispers of the Big Bang itself. This new sense, this ability to hear the universe through gravity, has the potential to revolutionize our understanding of the cosmos as profoundly as the invention of the telescope. Just as Galileo's first glimpse through a telescope revealed a universe teeming with stars and galaxies beyond our wildest imaginations, gravitational wave astronomy is opening up new vistas on the universe, revealing phenomena we never even knew existed. As we continue to listen to the symphony of the universe, we are likely to discover new instruments, new melodies, and new harmonies that will challenge our understanding of the cosmos and inspire future generations of scientists and explorers. The universe, it seems, is far stranger, more wonderful, and more harmonious than we could have ever imagined. The discoveries of the expanding universe, cosmic inflation, and gravitational waves have reshaped our understanding of the cosmos. We've transitioned from a static universe to one that is dynamic and evolving. This new perspective is a testament to scientific inquiry and a humbling reminder of our place in the universe. The expanding universe implies a beginning when everything was concentrated into a small point, the Big Bang, the cornerstone of modern cosmology. The tools and techniques used to explore the cosmos have also undergone a revolution. From powerful ground-based telescopes peering deep into the universe to space-based observatories like Hubble and James Webb, our ability to observe and study the cosmos has reached unprecedented levels of detail and precision. These technological advancements have been instrumental in confirming theoretical predictions and uncovering new mysteries, fueling a continuous cycle of discovery and innovation. The detection of gravitational waves by LIGO and Virgo has opened up an entirely new avenue for exploring the universe. Gravitational wave astronomy allows us to listen to the symphony of the cosmos, revealing events and objects that are invisible to traditional telescopes that rely on electromagnetic radiation. It's like gaining a new sense, allowing us to perceive the universe in a way that was previously unimaginable. As gravitational wave detectors become more sensitive and new telescopes come online, we can expect a wealth of new discoveries. We will delve deeper into the mysteries of black holes, neutron stars, and other extreme environments where gravity reigns supreme. We might even detect the faint whispers of the Big Bang itself, revealing the secrets of the universe's birth. The quest to understand the universe is a collaborative endeavor involving scientists from across the globe working together to unravel the cosmos's secrets. This shared pursuit of knowledge transcends borders and cultures, uniting humanity in a common goal of exploration and discovery. The continuous advancement of technology, coupled with the ingenuity and dedication of scientists worldwide, ensures that the frontiers of knowledge will continue to expand, revealing a universe more awe-inspiring and enigmatic than we could have ever imagined. The discoveries of the past century have transformed our understanding of the universe and impacted our perspective on humanity's place within it. We are but a small part of a vast and ancient cosmos, teeming with billions of stars and galaxies. This vastness evokes awe and wonder, reminding us of boundless possibilities. It inspires humility and highlights our remarkable ability to contemplate the universe. As we explore the cosmos, we carry our human spirit and thirst for knowledge. The journey of cosmic exploration is a testament to humanity's best. It enriches our understanding of the cosmos and our place within it.